Okay, let's give it a start for today. Welcome to class lecture 6. And before I I guess I can share the screen on this. I have a bunch of announcements to make. So I guess we should get started. Does anybody have any questions before I start? No questions. Okay, then let's get started. I have a bunch of announcements, and the ones I managed to remember to type here are only some of them. So I have to use my notes for some. Let's go through what's typed first. Okay, your homework is due this Friday at 11:59. Be sure to go to office hours if you have any questions or ask in Piazza. If you or think it's too personal a question, ask to the instructors directly instead of to the whole class. If you have any questions about any of the examples in the pre-recorded lectures or any of the explanations, please email me via Piazza as soon as possible, and I'll try and go through that example in class on Thursday to make sure everybody understands it. If it's not possible for you to go to virtual office hours or me or the TAs, go to somebody's office hours and they can go over it with you. If you think my English is unclear, please ask questions during class, and I can try and restate what we're doing or the problem a second time and see if I can get it better for you. Particularly if you think I speak too quickly. Sometimes I do. Okay, typically, I don't know if everybody realizes this or not. I try and put the slides for the class without the work, just the basic slides. I try and put them out at least the night before or maybe early in the morning thereof, because I keep changing them pretty much up to last night. So I try and put them out there so that if you have a chance and want to download them so that you can take notes on them directly, they're available to you. After class is when I put out the ones that have either my scribble or the ones with the proofs in blue that'll help you, that are the complete proofs. Okay. Extra problems. Some people indicated that they'd like to get more of a flavor of the kinds of problems that might be on quiz 2. That's really hard to say. Let me say the following. I will not ask you anything that is not covered in either the pre-recorded lectures, the class, or the discussion sections, or in the book. So that's why we tell you to read the book, watch the pre-recorded lectures, and come to class. Okay, but they're usually going to be of several types. Well, either something similar. Now, let me say that clearly. I most likely, although not impossible, will not ask you to prove anything directly that is done either in class, on your homework, or in the pre-recorded lectures. But I will ask, if you look at my list of things here, I will ask you similar related questions, okay? Now, this is the book problems. Now, what are the book problems? What do I mean when I say that? In the book, there are practice problems. They prove some of the propositions directly, showing you how to do a proof. And their homework, their problem exercises at the back of each chapter. The exercises that have the numbers in blue have at least partial solutions in the back of the book, so that if you try and do them, you can tell if you're on the right track or not. I suggest going through a lot of them. In chapter 2, the only ones like that I don't care to do are the ones that say do informal proofs. They're not the kinds of things you will be asked on an exam. You'll be asked to do real proofs. So anywhere that it first does, like in the beginning sections where it does an informal proof and then a formal proof, the formal proof is what you have to be able to do. So read it over. If you don't understand any steps or where it comes from, ask. Furthermore, what you should do is spend a few minutes, I don't know, I should say, a few times in each evening saying, can I do this proof? Let me try it. Can I do this proof? Let me try it. The quiz is 9 days from today. Okay, so this is lots of time. The last new material will be done today, and there's lots of time to study and ask questions. Okay, what's the next thing here? The practice quiz does not cover all the material that'll be on quiz 2, nor is it the same length. We had this discussion at the end of quiz 1. I'm reminding you of that. I believe quiz 2 says that at the beginning. It will be 9 days from now on Thursday during class time, just like before. Could you mute yourselves, or do you want me to do it? I'd rather you did, but I can. Okay, I will. Okay. I will take your thoughts into considerations. I should say not just your thoughts, that your strong feelings about the length of the exam. The quiz covers sections 2.1 through 2.5 inclusive. 2.6 or anything else is not included on the exam. Ask questions if there's anything you don't understand. Okay. Someone asked a question about induction, saying, can you take Pn given and Pn minus and prove Pn minus 1? The answer is never. Okay. If you assume Pn, when you prove, well, that's not on this. Hang on a second. I'll go through that when I'm done with the questions, the announcements. Okay. What are some of my other announcements here? I want to know if everyone can make at least some of the office hours from either me or the TAs. If you cannot make anything anytime in the week, please send email. I will try and modify office hours or add to them until everyone can make at least some office hours. Okay. If you can't make anything anytime during the day, that's kind of a problem, because I try to let the TAs have their evenings for their own studies. But if you absolutely can't, send an email via Piazza to me, and you could also include why you can't do it any other time. But I will try and accommodate. We need you to be able to ask questions and get help. Okay, I think I got it all there. If you want specific type exam questions to study, I don't know what to tell you, because there will not be anything exactly the same as on the exam, but I guarantee you everything will be on material that we cover. Now, I understand that some people think I do too much like the pre-recorded lectures. I hope that's not a current view, since I don't do any of the same proof problems. I try to make sure they're all different, but to just go over what the material is that's covered. Tell me if you think I'm covering too much of the same things, because I'm covering the same sections, but trying to do lots of exercises to give you experience and have you practice. But tell me if you think it's too much the same, and then I'd be happy to change it some. Okay, I think that's it for announcements. So let's go back and review the steps of an induction proof and why you cannot assume something is true for Pn and then prove it for Pn minus 1. Okay. Basically, somebody please mute whatever that issue is. Okay, so basically in an induction proof, you're not proving it for all cases. Basically, the basic hopscotch for an induction proof says you start with the base case and then you hop along from one to the other to the next one. And that's why when you assume P sub n minus one and prove P sub n, you're saying that if I know it's true for any one before, I can prove it infinitely many times and I'm done. You can't say that if you start out with one and then go down. That doesn't prove anything. So it's always the case that you have to assume. The induction hypothesis says assume that P sub n minus true is true, or assume that Pj is true for all from the base case to just below. That includes n minus one. That first case for strong induction, you basically do in the case where you need more than one of the lower cases, the lower orders. So for example, if you have an induction that says prove something is true about Pn based on Pn minus one and Pn minus two, in that case, you need to know it's true for Pn minus two and Pn minus one. So then you use the strong induction, but otherwise it doesn't matter. David, question. I can't hear you. Maybe that's my fault.
He's muted. I
Okay.
can't either.
Can you hear me now?
Yeah.
Okay, sorry. So can you use an induction proof to prove that like from -1 going down to negative infinity? Could you use induction there and then use the n and the n minus one?
I've never been asked that question before. Typically what you would do is you would restate the predicate so that you can state it in terms of positive integers. Okay. Then you put the negative into the predicate. Okay. Dane.
Are there any indications in a given problem to where strong induction is preferable to weak induction? Because I know sometimes it's easier to prove one thing with weak or strong versus weak and vice versa.
Well, as I said, if you have any kind of induction where P sub n is based on P sub n minus one and P sub n minus two, for example, then it's definitely the case that strong induction is your ticket. In other cases, it's whatever feels best at the time.
Thank you.
Christopher.
Hi,
Remember to put your hand down when you've asked your question. Yes, Christopher.
I'm just wondering if we have, say, a recursive sequence that has two base cases, like the Fibonacci sequence. Do we need to prove a sub 1 and a sub 2, or is it enough to just show?
No, you have to prove a sub 1 and a sub 2.
Okay.
They are your base cases. If you need them both, you need to prove both.
Okay. Thank you.
But if it's given to you, there isn't much to prove there on, depending upon what the predicate is that you want to show. Okay. Okay. Let's move along here. So obviously those are the steps involved, and I want to review induction by doing a couple of induction problems before we move on to the new material today. So let's do that. So here's one of your questions right there. Let a sub n equals a sub n minus 1, 2 times a sub n minus 1 plus a sub n minus 2, where a sub 1 is 5 and a sub 2 is 10. Use induction to show that for all n greater than or equal to 3, a sub n is less than 3 to the n. Now, this is a little different kind of induction proof than you've done before. Okay. So P sub n, what would P sub n be for this case? By the way, I know I told you to always raise your hands, but when I ask you for interaction on a proof, it's okay to speak, to unmute and speak. And I would be delighted if all bazillions of you spoke at the same time and had it right. So what's P sub n?
2a sub n minus 1 plus a sub n minus 2 is equal to 3 to the nth power.
Is not equal to it. That's equal to a sub
less
n.
than.
This is it right here. That's what you want to show. That's a good try. You never get marked down for trying in class. It doesn't have to be right. It's always okay to contribute. Okay. So what this says is for n greater than or equal to 3, a sub n is less than 3 to the n. That's what we want to show. Okay. Okay. Now, it's not true in this case for A1, is it? No. Our base case for this problem is what? N equals 3 for our base case here. Okay. It's not true that A1 is less than 3 to the 1. And it's not true that A2, well, it is true for A2. A2 is less than, A2 is 10. Nope, that's not less than 3 squared. So this conclusion, this predicate is not true for A1 and A2. So that's why we have to look and say, okay, now base case. Can you all see my scribble here okay? Or do you like a heavier one?
It's good.
Good,
That's
okay.
visible to me.
So base case here is P3. So P3 is equal, A3 is equal to 2 times, what's A2 is 10, plus A1, which is 5. So A3 is 25. And that's strictly less than 3 cubed, which is equal to 27. So P3 is true. Okay. Okay, now this is a little tricky. I just want to make sure you understand how we're going to get at this. So the next one is now, what do we assume for the induction hypothesis? Do we need to prove A4?
Assume n less than k is true.
We need to prove A4 also. Why? Because when we're proving the general case, we need to know it's true for a sub n minus 1 and a sub n minus 2. Okay, so we can plug in what goes there. So we need to prove it for A4, at P4. So now we show P4. And that's equal to A4 is equal to 2 times A3 plus A2, which is 2 times 25. We figured that out. Plus, what's A2? 10. Whoop. Okay, that's equal to 60. And what is 3 to the 4th? 3 to the 4th is equal to 3 times 27.
64.
So it's equal
81.
to
81.
81.
81, good, which is less than 81. So P4 is true. Now we can do the general case. Here was the case where we had to show it for 2 base cases. Why? Well, we're going to need both of them. Here's where we go. So now we say assume P sub n minus 1 and P sub n minus 2 are true. That's equivalent to using the strong induction here. So then we say, okay, so a sub n is equal to 2 times a sub n minus 1 plus a sub n minus 2. Now, what do we know? We know that that is strictly less than 2 times, what's a sub n minus 1 less than? A sub n minus 1 is less than 3 to the n minus 1 plus a sub n minus 2. What's a sub n minus 2 less than? It's less than 3 to the n minus 2. Okay. All right. Now we do some tricky stuff. So we have that's less than 2 times 3 to the n minus 1 plus, now this is going to be less than 3 to the n minus 2 is less than 3 to the n minus 1, isn't it? Because we're multiplying by 3 more. So that's strictly less than that. And this is equal to 3 times 3 to the n minus 1, or 3 to the n. So we have shown, a sub n is strictly less than 3 to the n, and p sub n is true. Hence, p sub n is true for all n greater than or equal to 3. Okay, questions? Kyle.
So I have two really short questions. The first one is, would this be considered a formal proof?
Yes, this is a formal proof.
Okay, and we're expected to do formal proofs on this homework as well, right?
Yes, you're supposed to practice for the quiz. Absolutely.
Thank you.
13 Leo Zong.
Oh yeah, I just kind of wonder why we need to show like two cases in the base case, like the P of 3 and the P of 4.
Good question. Good question. If I look at this, okay, it is not the case. Look down here. Down here, I used that both a sub n minus 1 and a sub n minus 2 were less than 3 to the n minus 1 and less than 3 to the n minus 2. If I didn't show that, okay, if I didn't do it for 4, then I would think this is true here for n greater than or equal to 5. If I said it was true for n greater than or equal to 4, then I couldn't say that, because if n was 4, then a sub n minus 1 would be 2. And it is not true that a sub 2 is less than 3 squared. Is it? No, because a sub 2 is 10. Okay, so the induction hypothesis for P4 would not hold, and I couldn't use it for later examples if I tried to show it. This base case, you have to show each of the cases for which this is not true. And it's not true for P3. I'm sorry, it's not true for P1, and it's not true for P2. Okay. So P3 and P4 are base cases. They're the first two for which it's true, and that I can use to do later computation. We use that right here. This step right here uses This uses it for a sub n minus 1. This uses it for a sub n minus 2. David,
Yeah, I was just wondering how we got 3 times 3 to the n minus 1 to equal 3 to the n, and I just understood it. Sorry.
okay, good. Glad to hear it. All right, let's go on. Okay. So I have a nicer proof there for it. We'll come back to that. You'll get that after class today. So here's another review practice proof. And this practice proof has to do with, we're looking at, this is phrased in a way that's a little easier to create P sub n, I think, and to state what they are. So this says, show that the sequence is defined by a sub k equal to a sub k minus 1 plus k squared for k greater than or equal to 2. Remember, you're not defining it for k equals 1, but you're saying a1 is 1. And the sequence defined by this closed form are equivalent. That is, that a sub k equals b sub k for k greater than or equal to 1. Okay, what is P sub n? P of n, not P sub n, P of n. What's our predicate? Right here. A
of n equals b of n.
Yes, B of n. Then you have to say for what cases, for n greater than or equal to 1. Now we need to prove that P of 1 is true. So let's do it. P of 1, a sub 1 is equal to 1. And b sub 1 is equal to 1 times 1 plus 1 times 2 times 1 plus 1. So what do we have here? All divided by 6. So what do we have there? We have 1 times 2 times 3 is 6 divided by 6, which is 1. So a sub 1 equals b sub 1, and P of 1 is true. Okay? Guillermo.
Yeah, so why do we use k is greater or equal to 1 for the predicate instead of k is greater or equal to 2?
Oh, because you're proving the equivalency. This statement says that's what you want to be true.
Okay.
Okay? It's not just the ones that you have to prove the induction for. You could use the base cases when it's true for the base cases. In our last example, it wasn't true for A1 and A2. The first case for which it was true was A3. So A3 and A4 became our base cases. Here we're saying it's true for A1 because that's what it tells us we have to prove. And we only have one case. We're not talking about A1 and A0 or anything like that. Okay?
Okay, yeah, that makes sense. Thank you.
Great. Put your hand down, please. Okay. So what's the induction hypothesis? Induction hypothesis is that P of J, I'm going to state the strong form, is true for J less than or equal to, well, let's see, 1 less than or equal to J strictly less than N. Namely, that A sub J equals B sub J, 1 less than or equal to J strictly less than N. Okay? That's the strong form. That means it's true for N minus 1. So now we say, okay, what do we have here? We have that A sub K is equal to A sub K minus 1 plus, then we want to prove it, plus K squared. Now, by the induction hypothesis, That's equal to B. So I'm sorry, we're proving it for N. Hang on a second here. A sub N is equal to A sub N minus 1 plus N squared. By the induction hypothesis, that's equal to B sub N minus 1 plus N squared. We use the induction hypothesis instantly here. Then the next case says, oh, well, I know what B sub N minus 1 is equal to. That's equal to N minus 1 times N minus 1 plus 1 plus 2 times N minus 1 plus 1 all over 6 plus N squared. We just do the substitution. Now the next step, I'm going to use what I have already. I'm going to multiply
Professor,
numerator and
on that-
denominator by 6 so I can put them all over common denominator and do rational addition.
On that last part, when you substituted in N minus 1,
Yes.
on the top of the fraction, isn't that all just being multiplied?
Oops, you're right. Thank you so much. Okay, thank you. That would have been bad. Okay, don't make those mistakes. Okay, so what do we have here? We have N minus 1 times N times 2N minus 2 plus 1, which is 2N minus 1. Plus 6N squared all over 6. Okay, onward. I'm going to go up here. That's equal to, I have a factor of N here and one of these N's that I can pull out. I don't like doing cubes if I don't have to. So we'll factor out N. And then what do we have? Well, we have N minus 1 times 2N minus 1 plus 6N all over 6. Okay, so we factored out an N. That's the distributive property. Distributive property. And that's equal to N. So we have, I'm going to write in small here. So we have N squared, 2N squared, 2N squared minus N minus 2N plus 1. That's the first factor, first term. And then we have plus 6N all over 6. And that's equal to N times, we have 2N squared minus 3N plus 6N is minus 3N plus 3N. Plus 1 over 6. You understand that factoring? I can't go to the next page because there isn't space there. I'm sorry, I didn't leave 2 slides for this problem. Egads. Okay. All right, so what do we have here? Well, if we factor 2N squared plus 3N plus 1, what we have is 2N plus 1, N plus 1 over 6. And do the arithmetic. Now, if you look, That's exactly what we're supposed to have there if I interchange the n+1 and the 2n+1 using the commutative property. Okay, so to say it's proved says that after all of this, this is equal to Bn. Now I have a nicer proof on the next page that I'll give you after class today. Okay, but we're working through it now just so you follow the steps. Okay, I'm going to start leaving more blank slides so I can do more. I can write bigger. I'm sorry that it's so tight. Do you follow what I'm doing here? Do you have any questions about this? Good. Okay, let's talk about something new. This is section 2.5, proof by contradiction. Proof by contradiction, which you've seen in the lecture, says that if you're trying to prove P implies Q, a proof by contradiction assumes P is true and not Q is true, and you end up with a contradiction. So you end up saying, well, that's impossible. It can't be because it contradicts that P is true, or it contradicts that something else that you know is true, like 1 is equal to 0 or something like that. So you make sure that you get there. Now it's different than the contrapositive proof. The contrapositive proof always requires P implies Q, okay? Contradiction proofs don't always assume that. Contradiction proofs, sometimes you just have a statement like a predicate statement, or you have a statement that says a proposition, okay? That's unambiguously true or false. And so you say, I'm going to assume it's true and prove it can't be, or I'm going to assume it's false and prove it can't be, depending upon the direction you want to go. We'll do an example of that momentarily. In a proof by contraposition, you have to have if P, then Q, so that you can say not P implies not Q, okay? So what you come up with in a proof by contraposition is you start out and you say, if not P, then not Q. You haven't assumed, I'm sorry, if not Q, then not P. You haven't assumed P is true there. You've just directly done a direct proof, and you don't get a contradiction, you don't get an impossibility. They're related, but not quite the same. Something else that occurs in this section that is proved in this section by the fundamental theorem of arithmetic. What is that? Every integer greater than 1 can be expressed as the product of a list of primes. So 4 is a list of 2 times 2. The same prime can occur multiple times. 6 is a list of 2 times 3. A prime number is also there because it is itself 5 times 1. Okay, so a prime number satisfies that, and a number that isn't prime satisfies that. Can you prove this using induction?
Probably not.
And can you prove it using contradiction? You need both for this one. Yes, it's in the book that way, but how are we using contradiction? In this case, contradiction would say there exists some number that can't be expressed as a product of a list of primes. So that number is either a prime, which immediately contradicts it because by itself it's already expressed as a product of primes, or it's not prime. And if it's not prime, it can be expressed as the product of 2 integers that divide it. And those integers are smaller. So if we pick the smallest number that could not be represented as the product of a list of primes, then we have, it's a product of 2 smaller numbers, each of which can be factored as the product of a list of primes. And that says that our original number can be factored as a product of a list of primes too. This proof is in the book, so I'm not going to do it. But that's the basic idea. You're using both contradiction and induction on that one. Okay? Because you're saying this is the smallest one that can't, for which it cannot be done. Okay? Stefan. I guess not. Okay. Here's an example.
Oh, sorry, my microphone was muted. Do you ever have to strictly say what kind of proof you're doing? Or can you just do the steps and then show your result?
Typically, you will say when you're doing a proof by contraposition, I'm doing this proof, I'm proving this by contraposition, because you know the equivalency of contraposition. If you didn't say that, it wouldn't at all be clear to the reader or grader that you knew what you were doing. If you're proving it by contradiction, then you want to say that I'm going to assume this and prove it's impossible. If you're doing it by induction, then yeah, you have to do that. So pretty much, and if you're doing it by cases, you want to do that. So in most cases, it's not that you have to because someone tells you, but to be clear about what you're doing, you state that. Okay? Okay. Proof by contradiction. So here we're going to assume P and not Q. So what does this say? This says if A is a rational number and B is an irrational number, then A plus B is irrational. So in this statement, what is the P predicate and what is the Q or proposition? What are they? Well, the P predicate is A is a rational number and B is an irrational number. That's P, both of them. A plus B is irrational, that's Q. So you want to assume P and not Q. So what are we assuming here? We're assuming that, excuse me, P is in Q and B is irrational, so it's in Q prime. So now P is equal to some A over B, A, B in Z. Let's say they're relatively prime. Remember what relatively prime means? They have no common divisors other than one. Okay? And Q is irrational, so we can't say anything about that. We're also going to assume A plus B equals C over D, C, D in Z is rational. And C over D are also relatively prime. This is assuming that's not Q. We're assuming not Q, and we're assuming P. Okay? Then what we have is that A plus B is equal to C over D, and that's by hypothesis. But A is equal, it can't be A. I'm sorry, this can't be A over B. C, D, let's say E, F. E and F. It's okay to say, what are you saying, by the way, when I do something silly like that? You cannot use the same thing for two different meanings. Is this clear now? I apologize for that one. Okay, so A plus B is equal to C plus D. That's by hypothesis. It's also equal to E over F plus B. B is irrational. I can't write it that way. So now we say, well, that means that B is equal to C over D minus E over F. Just subtracting E over F from both sides. Now we do rational subtraction. That's CF minus ED over DF. And that's rational subtraction. Okay, and that's equal to some M over N, where M is equal to CF minus ED. Why is that true? And that's in Z. Why is that true?
Closure.
Closure of the integers.
Closure under what?
Addition or subtraction.
Subtraction. and
Subtraction.
multiplication. Okay. And N is equal to DF, and that's in Z for closure again. And so that says that B is in Q. B is rational. That's a contradiction. Okay, that's a contradiction. Why? Because the hypothesis said B is irrational. All right, onward. Stefan.
Do you have to, I might have missed this, do you have to state that it has to be relatively prime? Because wouldn't it still hold true even if it wasn't relatively prime?
It does for this problem. I just generally do that because we're going to have some examples coming up that we need relatively prime. So I just automatically do it. If you don't need it, you don't need to state it.
Okay, thank you.
Okay. Fill this in. I want contributions here. I know how to fill it in. These are the steps in a practice proof. So we start out, we say, suppose we have an integer that's a counterexample. That is, what would a counterexample be? Come on. N would equal what?
3k plus 1.
Good. I don't know why that happens. And what would N equal?
9m plus 5.
Yes. 9 Mary plus 5. If we combine those two equations, what do we get?
3k plus 1 equals 9m plus 5.
Good. 9m plus 5, right. 3k plus 1 equals 9m plus 5. From which it follows that what?
Do you want to isolate either K or M, possibly?
Well, suppose we just say that that says that 3k minus 9m is equal to 4. We don't need to isolate them. You'll see why in a second. Okay. All right. That's also the case that, let's see, what shall we say? That means that k minus 3m is equal to 4/3. Now, why is k minus 3m an integer?
Closure.
Closure. Closure is your best friend, isn't it? Closure of integers under subtraction and multiplication. This can't be true. The left side's an integer, the right side's a fraction that can't be reduced to an integer. That's a contradiction. Okay? We follow the steps. We follow the steps. All right. Can I go on, or is it need to look at it longer? Okay. Here's a practice proof. Show there are no relatively prime integers a and b for which a squared equals 2b squared. What's the first step in this?
Assuming that there is a prime
Yes.
integer for which, yeah.
Very good. Assume there exists a and b in Z, A and B relatively prime, for which A squared equals 2B squared. Now what? What does the right side tell you about the left side?
A is even?
There, A squared is even.
A squared, sorry.
A squared is even. Then 2 divides A squared by the definition of divides. Okay, that implies, and this is by a proposition which, if this were a question were on a test, you would have to prove A is even. Why? We had a proof, we had a proposition that said if A squared is even, then A is even. And how would we have proved that one, by the way? Do you remember? Contraposition. Okay, so this is prove. So you'd have to prove this if it were on the quiz, but you should know it from before. Okay, so if A squared, if A is even, then A is equal to 2 times M for some M in Z by the definition of even, right? So then A squared is equal to 4 times M squared. So we substitute that back in and we get that 4M squared is equal to 2B squared. We factor out and we get that M squared is 2M squared, sorry, is equal to B squared. And what does that tell us about B squared?
It's even.
Yes, that implies B squared is even, which implies B is even. That's your proof that you proved already. Okay. What does that tell us? That says,
They both divide 2, or 2 divides both.
yes, 2 divides A and 2 divides B. So they would not be relatively prime. And that's a contradiction. Contradiction. So no such A and B in Z exist. What do we say? Q, E, D. Okay, do you follow that one? Yes, 2 divides both A and B. You can say it that way. All right. Good. All right, now we're going to talk about the pigeonhole principle, and then we're going to come back and do more exercises. I want to make sure, oops, break. If you have any questions, now's the time, but we're on break for 5 minutes. Grant. Oops, Ethan was first. Ethan. Yes.
So, well, I got the last proof. I do have a question about punctuating with QED.
Yes.
So do we have to do that for all
No.
the problems? Or?
Someone asked me about it in an earlier class, and they said they'd seen this on lots of proofs, and I figured, great, we'll do it.
What does QED mean?
It's Latin, and somebody here knows what it means better than me. It means quote, erat, something or another.
Is it like-
Quote, dictum or something like that. Demonstratum. Yeah, something like that. It's in Wikipedia. It means thus it is shown. Something like that.
All right. Thank you.
I used it for years without ever knowing what the Latin stood for. Grant.
So for the a squared equals 2b squared,
Yeah.
I'm confused why we would need to prove that a squared, or why we would need to do additional proof for that? Because couldn't we just say that b squared is closed under multiplication, and so therefore a squared is equal to 2 times some integer, and so it has to be even?
We don't know that a squared is 2 times an integer. 6 is an integer that's 2 times something. Basically, there's a proposition in section 2.1 or 2.2 that said, if a squared is even, then a is even. If a squared is odd, then a is odd, this kind of thing. And that was showing how to do proof by contraposition. If you're going to use it, I want you to be able to prove it. It's a good, straightforward proof by contraposition. It's not one of the hardest proofs you'll ever see. So go through it and look at it. One of the examples of the fallacious proof says, well, if you know a squared is even, then a squared is equal to 2 times some number q. But that doesn't say anything. That doesn't say that a squared, that q is even. And this is a much bigger deal to say if a squared is even, then a is even. Dane.
So I just wanted to confirm something about proof by contradiction.
Yeah.
So proof by contradiction, we assume P and not Q. And
Yeah.
that is the negation of P implies Q.
That
And
is,
we're showing that.
go ahead.
So I was just going to say that we're showing that the negation of the implication is false, and therefore the implication is true. And that's why this proves the implication.
I guess so.
I was trying to see why they're logically equivalent.
Yes. Okay. That's good.
Okay.
I hadn't thought about it that way. Okay. I guess there's another minute. Dane, put your hand down, please. unless you've got another question. Okay. We're on again. So the pigeonhole principle is something that is really handy for doing a lot of, working out a lot of problems. And doing a partial part of a lot of proofs. What does the pigeonhole property say? It says if K equal to M times N plus 1 objects are distributed among N different boxes, then there must be at least some box containing, there must be at least one box containing at least M plus 1 objects. So here we have the number of objects, the number of boxes, and one box contains at least M plus 1. We're going to do another statement of this that may make it a little clearer about where this comes from in a little bit, but let's do some examples first. If 29 tennis balls are given out to 4 players, then at least one player gets 8 balls or more. So if I were to put this in terms of the pigeonhole property, what is the number of objects? What is K?
29.
29 tennis balls. How many boxes do we have to
4.
put them into? What?
4.
4. Each person is a box in this case. See, that's box 1, 2, 3, 4. What's M in this case?
7.
7. So M plus 1 is 8. Now this is about the simplest version of a pigeonhole principle question that can be asked. Okay. Now I can look at that and say, well, if I pile all 29 balls into one guy's basket, then clearly it's the case. He's got 29, nobody else has anything. So when you spread them out the most evenly among the people, then you're giving each player 7 and there's one leftover ball. So one person has to get that. And that's where you get to the 29. Okay, we just did that. So here's a problem, pigeonhole principle problem. This one's a little bit harder. Okay. So given any 4 positive integers, some pair of them will have a difference divisible by 3. Now, in this case, how many objects do you have? I don't think we did this proof before. Did we? How many objects?
I think it was in the pre-lecture.
Oh, I didn't know that. Well, here you go. Given any 4 we have, do you want me to skip this and go on to another one, or should we do this?
More practice for me.
Do
Okay.
it.
Okay, how many objects? K equal 4. 4 objects. How many boxes?
2.
Ah,
3.
yep.
Mhm.
N equals 3. Why? I know you say, well, 2 was wrong, so maybe it's 3.
Well, it's because you need at least one box with a pair of 2.
That's
and all the other
right.
boxes have a pair of 1.
What it says there, you have 4 objects and that some pair will have a difference divisible by 3. So you want 2 of them in one box. We haven't figured out how to label the boxes yet, but we figured out that if I had 4 boxes, then they could each go in a separate box and I would have nothing. If I had 2 boxes, I could have 3 in one box and 1 in the other, but how would I don't know how to label them. So by the pigeonhole property, I've got to have 4 minus 1 is equal to k, not k, sorry, n times, what was it? What was my statement of it? M, n times m. Okay. So 3 has to equal n times n. Okay. So if I have one box, then m will be 4, and that's everything's in the same box, and that's not terribly helpful here. That doesn't solve it. So that says we're going to let m be 3, then m is 1, and m plus 1, the number of items in it is 2. So that's great. Now we have 3 boxes. I have to be able to label them. You must label them. It is not sufficient to just say, see, I have 3 boxes, so it tells me that. How will I label them to guarantee that however I put, these are any 4 positive integers. So I have to be able to specify the difference will be divisible by 3 by 2 of them in that box. So how will I label the boxes to guarantee something like that? And here's the biggie.
The remainders, maybe?
Say again?
Oh, the remainders, maybe? That's a guess.
The remainder. Well, that's called the division theorem, and yes, you're right.
Okay.
Learn the right name for it so you get full credit, okay? That's the division. That's right. You got it. Division theorem. So what are we going to divide by what? So we have some number, and we're going to divide it by what? How are we going to use the division theorem? Okay, we're going to divide by 3. So the division theorem says that if I have a number, let's say some number a, then a will be equivalent to 0, 1, or 2 mod 3. That's the division theorem, basically, okay? Or a is equal to 3 times q plus r, 0 less than or equal to r less than 3. So this is remainder 1, this is remainder 2, oops, and this is remainder 0. Okay, so I take my 4 positive integers and I throw them in the boxes by what their remainders are. And if they're in the box with remainder 0, suppose I1 and I2 are in that box. In that case, I1 minus I2 has no remainder. Okay, I1 minus I2 mod is equal to 0 mod 3, because each one is 0 mod 3. I don't have to go further than that. If it's in this box, then it says I1 is equal to 3 times Q1 plus 1, and I2 is equal to 3 times Q2 plus 1. So I1 minus I2 is equal to 3Q1 plus 1 minus the quantity 3Q2 plus 1, which is equal to 3 times Q1 minus Q2. Because I have a 1 here and a minus 1 when I multiply through. And that says 3 divides Q1 minus Q2, so it has remainder 0. So the difference is divisible by 3. I leave it to you to show the same thing when R is 2. Now you say, do I have to do that? Yes, you have to say what happens when R is 0, what happens when R is 1, what happens when R is 2. Okay. Any questions? Good, let's go on. All right.
Sorry, I have a question. Sorry.
Yes.
The
What would
previous
you like-
page.
What would you like me to call you since
Febs.
Feb?
Yes, ma'am.
Okay, I'll do my best.
It's okay. The previous page, please.
Yeah.
Yes. So I was thinking. I thought it was gonna be. Oh, I just answered my question. I thought the 3 boxes would be like 3 of the integers, but I just realized. I just understood it now.
Yeah, basically all integers can be divided into those 3 boxes. Because by the division theorem, all integers can have the form some integer is equal to 3 times the quotient plus a positive remainder of 0, 1, or 2. So all integers can be thrown into those 3 boxes.
Oh, got it. So that 0 is basically like 0 or 3.
Yes,
Man,
or
that's it.
6 or 9 or 12. So when I divide by 3, if there's no remainder, it goes into the 0 box.
Thank you.
Christopher, yes.
Sorry. When we use the pigeonhole principle, are we using like a kind of a different sort of quantifier other than like there exists? It seems like we're saying something like we can make something that shows what we want. I'm not sure exactly. It's not like a for all or exist statement, right? It's something kind of different. Is that accurate?
I'm not sure I understand what you're.
So
it certainly isn't a quantifier like for all and there exists an existence. This is sort of, like the division theorem says you can do this, and this is something similar, okay? But it doesn't tell you how to get there. In many of the problems that you use the pigeonhole problem for, you can use the pigeonhole problem to get you the number of things and the number of boxes, but you need to specify the labels on the boxes to say how you're going to put the things into the boxes. So any proof that you use the pigeonhole property, most of them, I won't say all, because the tennis balls we didn't need to, but most of them will require you to label the boxes so that you know which things to put in there and how they're distributed to guarantee the application, okay? I don't know if that answers your question. If it doesn't, we could try again. I'm not sure I understood it exactly, but not in class, okay?
Okay, thank you.
Anything else? Can we move on? Great, okay. Here we go. Here we got another one. Given any 7 integers, there will be 4 for which the sum of the squares of those integers are divisible by 4. How many objects do we have?
7.
6. Oh, 7, yeah. Sorry.
7. So we have k equals 7. There will be 4 objects in one box. So m plus 1 has to equal 4 by that standard. So that tells me since 7 is equal to n boxes times m plus 1, m is 3 here, so that 7 is equal to n times 3 plus 1, or n has to be 2. So that tells me this is sort of the reverse. There have to be 4 in a box that have a certain property. So now I'm going to divide it into 2 boxes. That's what that problem so far tells me. 2 boxes. How am I going to label them? 2 boxes, any 7 integers. What does the division theorem say? What do
Even or odd?
Say again?
Even or odd?
Even or odd. Well, the way I tend to say it is remainder 0 or remainder 1 when you divide by 2. That's the division theorem. You're right, even or odd is true. It's just easier with remainder 0 and remainder 1. Okay? Because we're going to use that in a minute. So this is remainder 0 or remainder 1. So now we are guaranteed. Okay, we have 2 boxes, 7 objects. One of them has to have 4 things in it. So now I have the problem, how do I guarantee that the sum of the squares of the integers in that box is divisible by 4? So here's where it comes in. If the remainder is 0, if that has 4 integers, then we have integer 1 is equal to 2k1, not k, sorry, to L1. Integer 2 is equal to 2L2. Integer 3 is equal to 2L3. And integer 4, these are i's over on the left here, 4 is equal to 2L4. Okay, they're even. So then I say, oh, I1 squared plus I2 squared plus I3 squared plus I4 squared. What's that equal to? It's equal to 4 times L1 squared plus 4 times L2 squared plus 4 times L3 squared plus 4 times L4 squared. And that's equal to, by the distributive property, 4 times the quantity L1 squared plus L2 squared plus L3 squared plus L4 squared. So that says that 4 divides the sum of the squares. And I'm not going to write it, even though you should, I'm not going to write it because I need to keep room to do the second case.
Professor Ellen, I think the first one you had was right. I think it should be k because L1 cannot be equal to twice itself.
I'm sorry, what did you say? K is the number of objects. It can't be a k.
But I'm saying like it could be any other number that is an integer because L1 cannot be twice itself.
This is an I, not an L. I'm sorry.
Oh, okay.
I's for integer 1 to integer 4. I'm sorry. My handwriting is that bad, huh? Okay. Now let's suppose, well, the deal is to make it clear, so I appreciate your asking. Thank you. Okay, so now let's do if R is 1, what do we do? If R equals 1, then all 4 of the integers will have remainder 1. So in that case, integer 1 is equal to 2L1 plus 1. Integer 2 is equal to 2L2 plus 1. Integer 3 is equal to 2L3 plus 1. And integer 4 is equal to 2L4 plus 1. Now what are we going to do? We're going to use a little notation here first. The sum of j goes from 1 to 4 of I integer sub j squared is equal to the sum j goes from 1 to 4 of 2 L sub j plus 1 squared. Each of them is squared. The squares, the sum of the squares. Okay, That's equal to the sum, j goes from 1 to 4 of 4L sub j squared plus 4L sub j plus 1. And if we look at that again, that's equal to 4 times the sum, j goes from 1 to 4 of L sub j squared plus L sub j plus 4. This last 4 comes from 1 out of I sub 1 squared, 1 out of I sub 2 squared, 1 out of I sub 3 squared, and 1 out of I sub 4 squared. This uses that summation notation that you may not be used to. So that's equal to 4 times, we have this summation, j equals 1 to 4 of L sub j squared plus L sub j. That's the summation plus 1, because I brought this 4, excuse me, I factored it. Okay? And that says that 4 divides the sum of the squares. So if we write it out, then we have for both possible cases, if either box has 4 integers in it, we've shown that the sum of the squares of those integers is divisible by 4. Okay? Yes, Fabe.
Yes. I was thinking, should the other integers, the one with the remainder 1, shouldn't it be 3 integers since we have 7 in total?
We have 7 in total, that's right. So the point is that either there are 4 in the first box, or there are 4 in the second box. So case 1 says, well, there are 4 in the first box. Case 2, suppose you pick the integers 1, 2, 3, 4, 5, 6, 7. Okay, then 1, 3, 5, and 7 would be in the second box, and 2, 4, 6 would be in the first box. So we don't care about the first box then because it doesn't have the 4 integers in it. But if I pick the numbers 2, 3, 4, 5, 6, 7, 8, then 4 of them have remainder 0, and 3 of them have remainder 1, and the 4 of them are in the box with remainder 0.
Got it.
Okay.
Thank
And I think we're over by 3 minutes, and I apologize. I have a lot more practice proofs. So what happens is on Thursday is a day to review the whole chapter. I have a lot of practice proofs from each of the sections that we talked to that I didn't get to, or that we can do that I didn't do at the beginning as a review. So please send me an email that says if you want to see anything that we did in class lecture or any of the proofs that were done in the pre-recorded lecture, if they're unclear, not your homework, I can't do that. Let me know, and I will do them in lecture on Thursday as part of the review on any of chapters 1 through 5. Okay, and in addition, if you've been struggling trying to do some proofs that we haven't covered that are in the book, let me know, and if I can squeeze time in, I'll do it in lecture, and if I can't do it in lecture, we can talk separately. I want you to try these proofs outside of class so that you can learn how to do them. So any of the ones you try, if you need help, if so, where are these notes posted on Canvas? If you look in the material for the week, where it has that the lecture, Tuesday lecture pre-recorded, Thursday pre-recorded, there's a box that says class lecture for the week, and there's one that says discussion. And if you go there, the slides for the lectures of that week, the night before, late maybe, that I give the lecture, I try and put the slides there without the answers, without the solutions. And then after class today, I clean them up a little, try and make sure I have material that if you ask questions about it, that I amend whatever I had there to try and answer those questions. And then I put them out. They're put out as PDFs. Okay. Everything. Now the pre-class lecture may have some of the problems that I don't get to in class, and you're welcome to try them. But you know, if you want to see anything, let me know and I can do them, as many as I can get done on Thursday as a review, because I know this chapter, learning how to do proofs, is new to so many of you. Okay. If you have any questions or want to ask me anything, stay after class and we can do it then. But everybody, you're free. I'm done. I'll see you Thursday.
Thank you.
Thank you.
Grant.
Professor
Thank you,
Elaine,
Professor.
should I call you Professor Elaine or Professor Cohen?
Professor Cohen works fine.
Okay, thank you.
Grant, I think you had a question.
Yeah, I have a question about one of the first examples. Would it be possible? It's just a specific
In this lecture or earlier in the week?
in this lecture.
Okay. Tell me how far back to go.
It was the one that
That
had
one?
two base cases. Yeah, this one right here.
Okay.
So I was working at it for like 5 minutes and I'm still actually, wait. Is it this one? Is there a second slide for this one? Like, did you?
Not that you have.
Okay, well, there was a part where it said,
Oh, wait, they got bigger somewhere and it's not there.
okay, yeah.
Got better?
Yeah. The part kind of near the bottom, the third-ish line to the bottom, where it's
We have shown?
Sorry?
Where it says we have shown?
The line above that one. The
A sub
two
n.
times, yeah, that one.
Yeah.
The 2 times 3 to the n minus 1 plus 3 to the n minus 2. How I can't figure out how that gets to 3 to the n. I
Sure.
got it down
Let's
to
talk about it a second right now. So it's clear that the first term here is the same as the first term here, and that follows from the induction hypothesis, okay? This is the induction hypothesis for A sub n minus 1, that A sub n minus 1 is less than 3 to the n. The induction hypothesis says that A sub n minus 2 is less than 3 to the n minus 2. Okay? Then we say, well, 3 to the n minus 2 is less than 3 to the n minus 1. True?
Yes.
Okay, so that's this n minus 1. 3 to the n minus 1 is less than 3 to the n minus, I'm sorry, 3 to the n minus 2 is less than 3 to the n minus 1. So we rewrite the first term, and then we say, oh, well, the second term is strictly less than 3 to the n minus 1. Now I can add them together.
Is there like a name that you could describe that as? I mean, how are we supposed to?
Well, 3 to the n minus 2 is less than 3 times 3 to the n minus 2, right?
Yeah.
Okay, well, that's what 3 to the n minus 1 is.
So if we have something that's less than something else, we can just say that
Substitute
that's
it.
equivalent to.
Yep.
Okay.
If
All
you're guaranteed it's less, be careful if there are negative signs in there, though. That's my only thing. When you multiply by minus 1, things can get turned around, but we didn't do that here.
Okay.
Christopher, I think it's your question next.
Yeah,
Wait a
just
second, I have to stop streaming. This is beyond class time, so I've got to stop.